So we've been in chapter 8 now. We're learning about bonding, and today what we're specifically going to get into is molecular geometry, polarity, a lot of review, some new stuff, as well as hybridization, which will be new to all of you. Same learning goal, big idea too that we've been talking about. And last time we made sure that we were comfortable drawing compounds that had single and double bonds, and I hope you spent some time at home practicing that, because today, in order to be able to determine shape, you need to be able to draw compounds with ease. What we didn't finish up last time are two sections here before we jump into shape. First up is bond energy. And we've talked briefly about bond energy. We indicated, for example, that double and triple bonds are stronger than single bonds. In terms of bond energy, this is how much energy is required to break 1 mole of covalent bonds between atoms in a molecule that are in the gaseous phase. Generally speaking, the greater the bond order, the greater the bond energy, the shorter the bond length. And you'll see that in the lab when you construct compounds. What's going to be very tricky to you is the formula, because it's probably the only time you do reactants minus products. So delta H, the change in enthalpy, is equal to the bond energy of the reactants minus the bond energy of the product. So this is one of the few times you do reactants minus products. And you can determine if a reaction is endo or exothermic based on the value of delta H. If negative, it's exothermic. If positive, it's endothermic. And shown here is a very simple example to determine delta H, and we're going to keep it very simple here. You'll see 1 or 2 of these in your practice quiz, and I'll also show you some of the interpretation type questions that I've seen on previous exams. So when you want to calculate delta H for this reaction, you really want to draw the compounds. You have ethane plus chlorine gas yielding ethyl chloride and hydrogen chloride gas. And the key to doing this correctly is to draw the structures. So you have ethane and chlorine, and you don't even need lone pairs here, keep it simple. And honestly, if you were really in a rush on your question, you could put sticks without hydrogens. You would know what goes on the end there. But if the lone pairs are bothering you, I'll smack them in real quick as such. Once you do that, you want to look at how many of each type of bond you have. So in ethane, I have 1, 2, 3, 4, 5, 6 C to H bonds. I have 1 C to C. I have 1 Cl to Cl. I have 1 C to C, 5 C to H's, and 1 C to Cl. And here I have 1 H to Cl. Now, if I had a coefficient anywhere, I'd have to factor that in and multiply everything I've got by that coefficient. Delta H is equal to the sum of the bond energies of the reactants minus the sum of the bond energies of the products. If you're doing this on part 1, the numbers are going to be very easy to manipulate, but you still want to simplify. And note I have 6 here and 5 here. I can get rid of those 5 and make 1. Note that I have the same thing here and here, so I'm going to simplify. Now I have 1 C to H, and the bond energy of a C to H is going to be 414 kilojoules per mole, and I have 1 mole of it. Yep.
Will we have like a different bond energy?
Yes. And sometimes, yeah, you'll be given that. The only thing that can be tricky is they might give you something for a single and a double bond, and if, for example, they gave you oxygen gas, you would know it was a double bond, so you'd use the double bond one.
And if we had, let's say we had like a coefficient, would you multiply the coefficient by how many of each bond you have, or by the bond energy at the end?
How many of each bond you had?
So like if we had like a 2 in front of the C2H6, we would have 12 C to H bonds and 2 C bonds?
Exactly.
Okay.
Then you have 1 mole here, and given in your notes is chlorine to chlorine is 243. And then 1 C to Cl. And then 1 mole of an H to Cl. And then just watch your math and you'll be fine. You can clearly see here that this is going to be 600 and something minus a greater value. So your delta H is going to be exothermic. Your reaction is going to be exothermic here because delta H is negative, and you get negative 113 kilojoules. Now, very often if they're asking you to calculate delta H off the bond energies, we're seeing it in part 2. I didn't go there in part 2 on your quiz because this is really going to tie into thermodynamics a little later in the year. But what you do need to understand, and I am seeing a lot of in the part 1 questions, is again, this negative value indicates that the reaction is exothermic. And we know that delta H is equal to the bond energy of the reactants minus the bond energy of the products. So the sum of the bond energies of the reactants minus the sum of the bond energies of the products. With a negative delta H here, which is greater? This one, right? A smaller number minus a bigger number will give you a negative value. That's what we're seeing. You'll see one in your classwork, couple in your classwork, in your practice quiz.
Would they ever ask a question like this and then give you delta S, you have to calculate delta G?
Yes. So when we get to thermo, we'll tie it in. And that's why I introduce it here, but in a part 2 fashion, I would hit it hard in thermo. You're exactly right. Not difficult. In the other class, we had covered this, so we did a simple do now. I'll show it to you because it asks some of the questions that you were addressing, but I don't want to take 20 minutes to go through it because, like I said, we were just a smidgy behind. It's somewhere. So the do now that they did was they calculated delta H for this reaction in which water was synthesized, but again, they had coefficients, and there wasn't really anything to cancel here, but this was the point I was making. You know that oxygen gas from honors chemistry forms a double bond, but they'll try and trick you up and give you both bond energies here. And that's the beauty of drawing. You're going to know to select this one, not this one. In addition, why would the bond energy of doubly bonded oxygen be greater than that of singly?
Double bond is stronger
Absolutely. Double bond is stronger and shorter than a single bond. It takes more energy to break the bond and separate the atoms. All right? And we can work through that one at the midpoint if you want to. One other piece that we left off with last time, and what we see on the AP exam now is picture after picture after picture. And that can get a little bit tedious. And this is one we've seen of a little bit. I put a really easy one on your quiz, but I'll show you a really hard one so you can see I was being nice. All right, two hydrogen atoms interacting. You are looking at that interaction in terms of energy versus the internuclear distance. Right here in the trough, where you have essentially the lowest energy point, you have the two hydrogen atoms at an optimal distance apart from one another. The bond length between two hydrogen atoms is 0.074. Typically you'd see it most likely as 74 picometers. And what you're seeing here is what happens when the atoms are too close together or too far apart. I want you to think about this in a couple different ways, and I want to take a look at one of your POGIL packets. Here's Model 2. It says a bond energy curve. And I would look over this POGIL packet over the weekend, but don't get too caught up in it. You just want to be comfortable reading the graph. So again, potential energy on the Y, the distance between the two nuclei on the X. It says the graph in Model 2 shows the changes in potential energy of a two-atom system as the distance between nuclei changes. Consider the potential energy of the system when the atoms are more than 15 nanometers apart. So here's 15, and when you're more than 15, describe the system's potential energy in terms of attractive and repulsive forces. What do you think? First of all, what's the potential energy at a distance of 15 or greater? Zero, not a trick question. And how would you describe it in terms of attractive or repulsive forces?
Could it be like either 5 is repulsive? Yeah.
Well, it's asking about more than 15, so what do you think here?
There are no.
Nothing.
Really nothing. Look at B. Consider the potential energy of the system when the atoms are less than. So here's 5. Well, it's hard to find it exactly. So less than 5 nanometers apart. So here the energy ranges, right? It goes from here till about there. And what do you guess is going on there? The atoms are too close together or too far apart? Too close. And if they're too close, what are they going to do? They're going to repel one another. It's like putting 300 kids in here. You'd be like, get out of my space. You'd push away. Same thing there. Circle the place on the graph where the system of the atoms is most stable. That's going to be right about there in the trough, right? Well, you circle on the graph.
Why would that be the most?
Potential energy is at a minimum, right? And the atoms are the perfect distance apart, so the attractive and repulsive forces there would be what? Yeah, balanced or equal.
But for like when the bond energy is positive and it's an endothermic thing.
Well, what they're showing you there, what you saw previously in calculating bond energy, is that was the energy required to break the bond and separate the atoms. What do you know about bond breaking, endo or exo?
Wait, what?
Do you think it's going to take energy to break a bond? Yeah, definitely endo. But here you're forming the bond. And bond formation or synthesis tends to be exo, hence the negative. You got it right there. Perfect. And again, like I said, this goes into excruciating detail. On Model 3, why do you think that the triple bond is this one right here?
In terms of distance,
Both. In terms of distance, you know a triple bond is shorter and stronger, so the energy is going to be at the lowest point there, the most negative, if you will, and the distance will be the shortest. This was a question that appeared on an AP exam one year. I really thought it was very mean. I was stunned, but now I think you'll be able to do it. I don't know how well the kids did on it a few years ago, but that's why we take the time to look through everything. It says the potential energy is a function of internuclear distance for 3 diatomic molecules, X, Y, and Z, is shown in the graph above. Based on the data, which of the following correctly identifies diatomic molecules X, Y, Z? Oh. X is hydrogen, and I know hydrogen's about negative 440. I don't know if you would remember it, but I knew to focus right there.
And Y is nitrogen.
Why?
I'm not really sure why, I just know it's strong.
Strong Y, because it has what kind of bond? Triple.
Okay. I know it's not.
And so that has to be the double. But it was a sneaky little question. And I don't know if they showed us how many kids got it right or wrong. I would imagine that the percent correct on this was just awful. I thought it was nasty.
Wouldn't the triple bond have a shorter distance between?
Well, keep in mind though, you're comparing H and N. So N versus H, that's a little tricky in terms of a comparison, whereas here you were comparing just C's. So it's an easier comparison, and that's why the question was so difficult. So I guess when you don't have the same atoms and you have different numbers of bonds between the atoms, really look at the lowest trough for the triple. But you raise a good point, and that's why one thing you really want to be sure of with classes from year to year and why the kids' scores are getting better and better is we're spending the time to make sure that you understand. And so if, for example, you look here, I said, how would other diatomic elements appear graphically? So what if I had chlorine gas? What do you know about the internuclear distance between 2 chlorine atoms versus 2 hydrogen atoms? Which has the larger radius? Chlorine, for sure. So that internuclear distance should be greater, so the curve should shift to the right. So those are the kinds of just tricky wikis they can ask, and that's why that POGIL packet is worth a look-see in regard to the graphs. All right, our real focus today, we're not going to do alkanes, alkenes, we don't cover this anymore. Our real focus today is on molecular geometry. Many of you drew a lot of compounds last year and determined shape and polarity. That will help you greatly this year. If you have not done anything with shape or geometry, and some of you, I found out second period, did not, you're going to need a little extra time this weekend going over shape and geometry. A lot of it should be review. You'll see some new shapes today, but that's not going to make or break you. But you have to be able to explain, and we're going to go through this very carefully. Molecular geometry helps describe either the shape of a molecule or the shape with respect to each central atom of a compound. It essentially describes how the bonded atoms are arranged around the central atom. It's all based on VSEPR. which is valence shell electron pair repulsion theory. And what you're going to see here is when I draw compounds, you've seen, for example, if I draw carbon dioxide, I will position those electrons as far apart as possible to illustrate their correct location. Now, you don't have to draw them perfectly. If you do this, that's perfectly acceptable. What I'm trying to illustrate is Vesper, and you'll use this theory to determine the shapes of molecules. Because electrons repel one another and lone pairs repel each other, you want to place them as far apart as possible. In addition, these are bonding electrons. These are non-bonding electrons or lone pairs, but we're going to consider them. We want to talk a little bit about electron groups. A single lone electron is an electron group. A lone pair of electrons is one electron group. A single bond is one electron group. A double bond is one electron group. A triple bond is one electron group. And you'll see where that comes into play right here. The electron group geometries will be new to everyone. They are not difficult. As I said, with electron groups, you can have a single unpaired, a lone pair, a single, a double, or a triple bond. Now, within that triple bond, you have 3 shared pairs of electrons, but it's one electron grouping, if you will. There are 5 electron group geometries, and that shows how the electron groups are oriented. If you have 2 electron groups, it's linear, 3 trigonal, tri means 3, 4 tetrahedral, tetra means 4, 5 electron groups is trigonal bipyramidal, 3 plus 2 is 5. This one will bother you. 6 electron groups is octahedral. And where that comes into play, and you'll see this better when you construct the molecules in the lab next time, is that when you have 6 electron groups, 1, 2, 3, 4, 5, 6, and then you consider this structure, if you drew all of those sides on, you'd get an octahedral type group. And you'll see that when we look at the images on the slides. The Vesper notation is a little tricky-wicky. I'm not going to use it very much. The kids don't like it, and it's not something you'll see on the AP exam, so I'm not overly concerned. I'll mention it. A is the central atom. X is the terminal atoms attached to a central atom. N is how many terminal atoms you have. E is the lone pairs of electrons on the central atom only. M is how many lone pairs you have. If in your structure you don't have any lone pairs on the central atom, I added in red that on the central atom it wasn't clear to the other class. You'll see the electron group and molecular geometries are the same. It's very important that you understand the difference between the two. They're going to ask you for molecular geometry, the shape. The electron group geometries can lead to the shapes and do help explain hybridization, but they'll ask you for molecular geometries. Before we go there, I just want to remind you of some basic shapes that you should have learned last year. You don't have to draw this unless you want to. This is a generic structure for an amino acid. What do amino acids make up?
Protein.
Proteins is correct. How many amino acids are there?
26.
20. 26 letters in the alphabet, but 20 amino acids.
All I remember is methionine. Is that like the starter one?
Yes, methionine. R is different for each amino acid. So glycine, the simplest amino acid, has an H here, and then you have different groupings of R for different amino acids. A single amino acid change can result in a disease. For example, in cystic fibrosis, a phenylalanine is missing. In sickle cell anemia, there's a single amino acid mutation. There are certain mutations resulting, for example, in Tay-Sachs disease, etc., in different proteins. So a single amino acid change can kill you, and when you group the amino acids together, it makes a little more sense. We'll get into that later in the year. In any event, where we're going here is I would like to know the geometry with respect to each central atom. Let's see what you remember. Go ahead, Chase.
Tetrahedral.
This one's tetrahedral. Faith, you got one?
That's what I was going to say, but hang on. I think the oxygen is bent.
Bent is correct. Go ahead, Andrew.
The nitrogen, is that trigonal planar?
Not quite.
Trigonal
Trigonal pyramidal. But you'll redeem yourself right here, because this one is,
Trigonal planar.
you got it. The difference between trigonal planar and trigonal pyramidal is, yeah,
Oh, okay.
you've got it. And which one don't I have there? Linear is correct. So right here, linear. Linear, 2 atoms attached, no lone pairs. Tetrahedral, 4 atoms attached to the central atom, no lone pairs. Trigonal planar, 3 atoms attached to the central atom, no lone pairs on the central. Bent, 2 atoms attached, 2 lone pairs on the central. Trigonal pyramidal is 3-1. And that should look familiar to a lot of you. Yes? We remember? Maybe? Who did you have last year? Yeah, you guys did drawing. Same. You did drawing and you did shape. Okay. No shape. No polarity. It's not, this is honors. This is exactly what I'm doing in honors today. It's the only time AP and honors do the same thing. It's like the only day. Yeah, otherwise the order is all different. All right.
They did the periodic trends.
They did it ahead of you.
Uh,
Alrighty. It's going to get a whole lot more fun.
Oh. That's not good.
No, it is. It's fun. Kids like drawing. This is like the easiest chapter, guys.
You said that about.
I know. Everything's easy to me. Alrighty. Please don't eat over the Chromebooks.
Nice. Oh, shit.
Oh, yeah. Alrighty. We are going to get into. Check out these shapes. Linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, trigonal bipyramidal, seesaw, T-shaped, linear, octahedral, square pyramidal, and square planar.
Is seesaw like
Put your seatbelts on. Actually, it looks like a little teeter-totter. Yeah, they don't have seesaws at playgrounds anymore. I guess kids probably went like flying off of them or something.
That was the fun part.
I know, they took away all the fun toys.
Do we need another bonding?
Some yes, and we'll go into that. So this table is going to be golden for you, and when we do the lab on Monday, it will come together better. Over the weekend, you are going to push to master geometry, polarity, hybridization. Nothing is difficult if you can draw.
Dr. Tape, I already passed you.
I have a minor in art, and I didn't care for geometry. All right. Actually, I like all math classes. Anyway, here we go. Huh?
I remember the quiz from last year.
Yeah.
Yeah, and then you had to do the isomers. Uh-huh.
In any event, I am going to draw all these examples for you, and we'll walk through the shapes. I'm going to show them to you. I've got a couple little videos where the molecules spin, and just so you can see the structures. But again, when we do the lab, you'll see it a little bit better. I think that will really help you. I'm going to go over the bond angles and why certain angles are smaller than what you would predict. First one up is very easy because electron group geometry and molecular geometry are the same, which they will be when you have no lone pairs on the central atom. So 2 electron groups, no lone pairs on the central atom, linear electron group and molecular geometry, bond angle of 180. You've actually already seen one of these, but we'll draw them both again. So what we're looking at for molecular group geometry here, this is going to be electron group, linear, and molecular group geometry, linear. For example, beryllium, chloride, this one's kind of weird because beryllium only forms 2 bonds, no lone pairs. Same thing with carbon dioxide. And this is 180 degrees. Yes?
What does it say in the electron?
Molecular. This is for the geometry. Sorry, little fluffy. And again, 2 atoms attached, no lone pairs, for a total of 2 plus 0, 2 electron groups. And that's why I said a single bond is 1 electron group, a double bond is 1 electron group. That's very confusing to the kids, so I'll usually go atoms attached, lone pairs on central. I think it's easier. All right, next up, and again, if you don't want to scribble all this down and you want to just watch, I did draw them out one year and I put them on Edline. I don't know if they'll be exactly the same, but they're probably pretty close. I think the structures are going to be the same. I don't know if I will have explained it exactly. I don't know. Cool. Next up for electron group geometry. First up is going to be trigonal planar, abbreviated. First molecular I'm going to do will be trigonal planar as well. For example, boron, trifluoride.
Do you have to draw it like that?
No. But I drew it like that because I want you to see you have 3 atoms attached, no lone pairs. You have a bond angle of 120 degrees. Sulfur trioxide would be another example. This one's a little unusual, but you're still going to get Same bond angle there.
So the sulfur on that one has an expanded oxygen.
You betcha. The other one I want to show you, still in the same electron group geometry, but the molecular geometry here is going to be bent or angular. For example, sulfur dioxide, which we saw the other day because it exhibits resonance. You still have 3 electron groups, but what you have here is 2, 1, 2 atoms attached, 1 lone pair for a total of 3. But what's interesting here is this bond angle here is a little bit less than 120. It's going to be 118 degrees. If they ask for the bond angle, they're going to have a range where you can be between, which is fine, but you have to explain why that bond angle is smaller. And that's what I want to make sure you can do.
Well, do we need to know the other way? Like, do we just need to know the degrees between the O's if it's bent like that? Like,
It's considered an OS to O bond, and that bond angle will be 118.
do we need to know the other side? Make that 360.
No,
Just add that.
they're just going to ask for that angle.
Okay.
Why is that the way that you draw that then? Like,
Well, you still have 3 electron groups, so I sort of drew it upside down. I don't know if that's what's confusing to you. This could have been like this,
yeah.
so you could spin it. It doesn't matter. But the key here is, why might this bond angle be less than this one?
Because they each have 1.5.
Oh, because the terminal atom has electrons that repel the other ones?
Because they each have 1.5 bond.
Because that's just the way it is.
I wouldn't write that. What do you know about electrons in bonds or lone pairs of electrons? They're going to do what to each other? They're going to repel a little bit. And what do you think repels more, a lone pair or a bonding pair? Have it a lone pair. So a lone pair, it has like a little more wiggle room, if you will, and they can push off each other a little more and just spread out a little more. They're not as confined as a bonding pair. And so what happens here, and this answer I'm going to write across, but it only goes to this. The lone pair of electrons repels more than a bonding pair compressing the bond angle.
Okay, Dr.
I'm fine.
That's exactly what they said.
No, they said the bonding pair.
No, I didn't.
No,
I
they
said
said
this.
that
I said
exact
the terminal
thing.
atom has a lone pair of electrons that repels the...
It's not the terminal
Oh, that's right.
atoms.
You said
It's
terminal.
this lone pair.
I meant central. I just said the wrong one.
Well, how's she know?
But I pointed to the sulfur.
How's she
Oh,
know
she
that?
knows.
You pointed at the board? I'm sorry if you had it right. That's right. Just do it right on game day and you can rub it in my face. It'll all be good. I'd be happy to have it rubbed in my face. But yeah, it's this lone pair.
Looks like a person.
I just, for some reason, terminal makes me think it's the inside one. Like,
No, but terminal means
Yeah, I
when
know what
somebody's
end
terminal,
is.
they're close to the end.
oh.
Right?
I was thinking terminal like in an airport, how it's like in the inside.
No, the terminals are going to be what gets you outside, right? So they're at the ends.
I guess I just misunderstood what that word meant.
Yeah, it means end. Terminal. If somebody's terminal, they're nearing the end.
Wait, so those lone pairs on the central
Oh,
atom,
wow.
they repel the...
They repel each other more than bonding electrons, so they're pushing, and that's what compresses the bond angle. Guys, let's refocus. It was an excellent
So
question.
those two lone pairs, those two electrons are basically like pushing each other apart,
They're
causing the other two bonded atoms to kind of.
uh-huh. It's sort
So
of
it's
like,
kind of like when you're pushing a twig enough, and then eventually it just snaps. A twig.
well, like, let's say you were trying to carry something like this way out, and somebody's really pushing down on you, and all of a sudden it's going to start to go down, down, down. It's the same thing. So when you walk around like with a book on your head, you're supposed to walk perfectly straight. Nobody does that. They start to scrunch a little bit, and their arms go down a little bit. It's the same type of thing. What?
He's being a bambi. Don't listen to him. Don't listen to him. He's being a bambi.
All right. Let's keep going here. We're going to see this concept again. If you have 4 electron groups, your electron group geometry here is going to be tetrahedral. And there'll be 3 different types of members to this family. For example, if you just had methane, which you would have seen last year, you're probably going to draw it flat, which is fine. Just be careful. This molecular geometry is the same as the electron group geometry because there are no lone pairs on the central atom. So what we have here is 4 atoms attached, no lone pairs. But when you construct this in the lab, it actually looks like this. I'm going to hold it up. So what you have here is not an angle of 90. It's clearly more obtuse than that. And the bond angle is actually 109.5. Sometimes you'll see it drawn like this, where this bond is coming at you, and this bond is going back into the board. And this angle is 109.5 degrees.
That's what, when we had to do the project last year and I got them from that website, do you remember how confused I was when there were all those stripes and like shaded boxes
Yeah.
and stuff? It was super confusing.
Well, I did something on your quiz to make the structure easier. I didn't want to freehand it, but I'm going to show it to you so you know exactly how to read it. There won't be surprises are not fun on quizzes. Now, if you have a 3-1, your molecular geometry, and this you would have seen last year, is trigonal pyramidal. And a good example here is ammonia. I'm going to draw it flat. Now we've established when you have 4 electron groups, the ideal bond angle is 109.5. However, this bond angle, H to N to H, and this isn't drawn to scale here, is actually 107 degrees. Why might this angle be less than that one?
Because the lone pair on the central atom repels the electrons in the terminal atoms and pushes them down.
Almost. But you've got to get, you're almost there. Let's go over what she had, which was solid. The lone pair of electrons on the central atom repels more than the bonding electrons,
Okay.
compressing the bond angle.
Okay.
It's going to be golden, I promise.
I'm gonna get it. I'm gonna do it.
I can't beat you. I'm
She's gonna beat it into us.
I adore you, and I'm too little. All right, we're on video. Okay, I'm teasing. Bent. This is a 2-2, and I didn't write 3-1 on there. Let me smack that in so you're crystal clear. And note 3 and 1 make 4 electron groups. But this one is going to be a 2-2. Now, I'm going to tell you that this bond angle is 104.5 degrees. Why?
Because the two lone pairs of electrons on the central atom repel more than the bonded electrons, compressing the angle.
But why is this angle smaller than this one?
Because there's two lone
So what do you
pairs.
think those lone pairs do to each other?
Repel.
They repel each other. So that's the key. The two lone pairs of electrons repel each other, or you can say that the lone pairs of electrons repel more than bonding electrons and repel one another, further compressing the bond angle. So you've got the lone pairs repelling more than the bonding electrons, and they repel each other for a smaller HOH bond.
Yeah, for real. I literally could recite it.
That's all right. You're going to have it on game day, and that's what's important.
Are we gonna do practice tests?
Huh?
Yeah, we do have to be practice tests, right?
Oh, for real game day?
Yeah.
Yeah, we get you ready.
Yeah.
All right. Couple more.
Yeah.
Here's going to be the new ones because you haven't seen the expanded octets until this year. So what we're looking at here is 5 electron groups or 6 electron groups. With 5 electron groups, you're going to have trigonal bipyramidal electron group geometry. You can have trigonal bipyramidal. You can have seesaw, T-shaped linear, and I'll show you what these look like. With 6 electron groups, you have octahedral, square pyramidal, square planar. Now here, the bond angles are 90, 120, or 180. They usually don't ask these bond angles. I did ask a bond angle on the quiz, but I gave you so much information that you didn't have to know it exactly. You'll be able to select it without it. These bond angles, you want to know. So with the expanded octets, let's look first at the electron group geometry of trigonal bipyramidal.
How does the shape that's the same, like trigonal bipyramidal and trigonal bipyramidal, have 3 different angles?
We'll take a look at that. You'll see it. You'll see it. Go ahead, Sam.
So the angles that we need to know are basically those from the shapes that we learned in honors.
Yes, except 118 we really didn't touch on.
Okay.
All right. First one up. Your molecular geometry, whenever you have no lone pairs, is the same as your electron group geometry. So this is going to be trigonal bipyramidal. So for example here, you've got phosphorus, pentachloride, yeah, I almost wish I had hydrogens, I agree. 5 atoms attached, no lone pairs. And this is why mastering drawing for today was really important. The next one up is seesaw, where you have 4 atoms attached, no lone pairs. Sulfur, tetrafluoride, and if you didn't do an electron count, you might have missed the lone pair on sulfur. Be careful. you're going to see that it has like a little triangle. I'll show you what it looks like. It's hard to draw perfectly.
Okay.
Yeah, you'll see it. I'm going to show you some pictures in a few minutes.
So it's seesaw because it has a lone pair and the central item?
Yeah, four attached, one lone pair. The angles are really tricky. I'm not going to draw it to scale.
So the lone pair added to the number of atoms attached always equals which electron group it is?
Yes, 4 plus 1 is 5, 5 plus 0 is 5.
What's the angle?
That's confusing. Let it go. All right. The next one in this family, if you will, is T-shaped. And with T-shaped, for example, chlorine, trifluoride, and again, if you didn't get an electron count, you might have missed the 2 lone pairs on the central atom. This is a 3-2. Again, 3 plus 2 is 5. And it looks like a T on its side. And you'll see that in a minute.
Why do you draw it like that?
Because it wanted it to look like a T or you'd be upset with me.
Why is this that?
But you could put the top.
Oh, look, you're going to see it looks like this. Chill, chill, chill.
Okay.
All right. And then finally, you've got this weird linear. Xenon difluoride. What the heck? And these atoms are in a line, and then these lone pairs make like a triangle. But again, you've got a 2-3.
Is it not bent because the electrons don't repel each other because of equal numbers?
They do repel each other, but they place themselves in positions as far apart as possible to minimize repulsion.
Gotcha.
All right, and I'll show you the octahedral, and then I'll show you all the pictures so you can see better what they look like. In regard to electron group geometry, we've got 6 electron groups for octahedral. For the molecular geometry, again, this first one will be the same, and we've got sulfur, hexafluoride,
What's the most expanded you can make an octet?
6 bonds,
Oh, so
6 electron groups, so 12. So again, you've got a 6-0, 6 electron groups. If you have a 5-1, you've got square pyramidal. So for example here, I skipped the lone pairs. You
Yes.
better not. I won't, because then you'll say, but you did it. I can see it now. Forgot to do it on the AP exam, Dr. Kalish, because you were lazy. It's all your fault. All right. 5 atoms attached, 1 lone pair, again 6 electron groups. And then last but not least is the square planar, and you'll see the designs in just a second now. And this is going to be xenon, tetrafluoride, You got it.
Are they top and bottom?
Yeah, you'll see why. But again, they all have 6 electron groups. I know. Let's take a look at some of these images.
The structure around a central atom is determined principally by minimizing electron pair repulsions. 2 bonding electron pairs around the central atom result in a linear structure. Carbon dioxide has a linear structure. The bond angle for a linear arrangement is 180 degrees. 3 bonding electron pairs around the central atom result in a trigonal planar structure. Boron trifluoride has a trigonal planar structure. The bond angles in a trigonal planar arrangement are 120 degrees. When one of the 3 electron pairs surrounding the central atom is a non-bonding pair, as in sulfur dioxide, the resulting structure is known as bent. 4 bonding electron pairs around the central atom result in a tetrahedral structure. Methane has a tetrahedral structure. The bond angles in a tetrahedral arrangement are 109.5 degrees. When one of the 4 electron pairs surrounding the central atom is a non-bonding pair, as in ammonia, the resulting structure is known as trigonal pyramidal. When 2 of the 4 electron pairs surrounding the central atom are non-bonding pairs, as in water, the resulting structure is known as bent. 5 bonding electron pairs around the central atom result in a trigonal bipyramidal structure. Phosphorus pentafluoride has a trigonal bipyramidal structure. The bond angles in a trigonal bipyramidal
There's your bond
arrangement
angles.
are 90 degrees and 120 degrees. When one of the 5 electron pairs surrounding the central atom is a non-bonding pair, as in sulfur tetrafluoride, the resulting structure is known as seesaw. When 2 of 5 electron pairs surrounding the central atom are non-bonding pairs, as in chlorine trifluoride, the resulting structure is known as T-shaped. When 3 of 5 electron pairs surrounding the central atom are non-bonding pairs, as in xenon difluoride, the resulting structure is known as linear. Lone pairs of electrons take equatorial positions preferentially. 6 bonding electron pairs around the central atom result in an octahedral structure. Sulfur hexafluoride has an octahedral structure. The bond angles in an octahedral arrangement are 90 degrees. When one of the 6 electron pairs surrounding the central atom is a non-bonding pair, as in bromine pentafluoride, the resulting structure is known as square pyramidal. When 2 of the 6 electron pairs surrounding the central atom are non-bonding pairs, as in xenon tetrafluoride, the resulting structure is known as square planar.
And that gives you a better idea of all the shapes.
The structure around a central atom.
But the other thing I wanted to show you, linear, trigonal, planar, tetrahedral, trigonal bipyramidal, there are your angles, octahedral. And here's your tetrahedral family, if you will, with trigonal pyramidal. You can see the triangle, but it's making a pyramid, versus V-shaped or bent. We usually just say bent. Here's trigonal bipyramidal, seesaw, T-shaped, linear, and that's all they've got. And these are a little bit hard to see. They're like blurry, so I didn't really think it was a great idea to pump them in your notes. Do you want me to put those shapes in your notes, or doesn't really matter? right, because you don't have to draw them perfectly, so I don't think it matters. All right, let's take a minute to try and do the problem in yellow. Give it a shot. You just want to indicate what it is. What
Just the
shape
shape.
is, yeah.
Okay, cool.
All right, so let's take a look at this one. Again, just be careful on your count. You have bromine difluoride ion.
I could not see.
You've got 7, 4 times 7, 35, and one more is 36, right? Now, be very careful. I can't tell you how many brilliant kids I've had, and I've had a lot, who forget that. In addition, we're at 24, 26, 28, 30, 32, and I need 2 lone pairs. What's the shape?
Square planar.
Square planar is correct. Okay?
Is it difluoride or tetra?
Tetra. Bromine tetrafluoride ion.
I'm just making sure I'm not going crazy.
Do we have to draw it like that?
No. 4 bonds, 2 lone pairs, brackets, and an ion charge. You typically see that on elements from group 15 or 17, and you will have an odd number of total electrons. Go ahead.
Is there like practice on the rest of like the practice tests and stuff on drawing ions and stuff? Because I always forget.
Yeah, there's tons of practice in your textbook and at the end of the chapter. Absolutely. All right, we're going to take a break now. I want you to make sure over the weekend you master compound drawing and shape. We've got a smidge more to do on polarity, which is easy. hybridization, which is even easier, sigma and pi. And we'll do that in the second half. It'll take maybe 15 minutes, but I want to give you a break at this point, and then we'll come back and finish up.